Hey, Vineet, are you there?
Hey, Gautam. Yeah, I'm here. One second. I'm just hooking everything up.
No problem. Take your time. Yeah.
One second. Dang, empty class today.
Listen.
Oh, yeah, our video is on. Can you see? Can you hear us, Gautam, from the owl?
Yeah, yeah, I can hear you. You can hear me?
Yeah, yeah.
Now I can't hear you properly.
No, I haven't said anything. I haven't said anything. Yeah, yeah.
Oh, it's like the volume is going up and down. Now it's good. Yeah, now it's
Sounds good. Okay. Let me turn on it.
Hey, Vineet, can you hear me?
Yeah, we can hear you. We can hear you. Just putting up the monitor. One second. The screen.
Yeah, yeah.
I think you can see everyone. Can you?
Yes.
All right. You can see your screen. Minimize this. I think things are recording now. All right, everything should be recorded. Okay, I think we're good. We'll go ahead and get started.
Yeah, so I wanted to do, there was a lot of stuff that was taught in the class a couple of days back. And I did want to review some of the important concepts, just drive it in so that you guys know what is important, at least to carry on from this lecture. So before that, any questions you guys have before we get started? Okay. So you can hear me, right?
Yeah, I want to hear you. Yeah.
Okay, okay. Yeah, so basically what we talked about was the fact that as chips are scaling because of Moore's law scaling, the number of terminals coming out of the chip is basically increasing. However, the package is not scaling sufficiently. So you have limited number of channels on the package, but you have a lot more terminals coming out of the chip. And therefore, the only way to use the minimal channels on the package to communicate between two chips is to basically take parallel terminals and convert them into a single serial terminal using something called as a SerDes. And what that entails is that the links now operate at much higher frequencies. And when the links start operating at higher frequencies, what happens is, depending on how the wavelength of the signal that is traveling along the link compares to the length of the link can behave either as a transmission line or as a waveguide or as a lumped element, right? Depending on the frequency. And generally, it will generally not behave as a lumped element because in most cases, even if you consider a digital signal that's like 1 Gbps, because digital signals tend to be nonlinear because they have very sharp transitions, they tend to have higher frequency components, and in the end, the link always tends to behave as a transmission line. Okay, so I think that's like the main kind of I would say concept to understand as to why signal integrity actually matters when you go to when you go to advanced uh, technology nodes. So fundamentally, you basically have three regimes depending on how the wavelength of the signal compares to the dimension. So, for example, any of these kind of links, it has basically it has some particular length, say along the z direction, and then it also has a cross section along the XY plane, and the cross section can be anything. I haven't really talked about the different kinds of waveguides because I felt that that's more in EM. But there are so many different kinds of waveguides. You can different kinds of cross sections you can think of. For example, you can think of a coax. You can think of a simple case where there's just a metal line which is sitting on a substrate with some ground plane below, and so on, right? But in any of these cases, what really matters is how these dimensions, so for example, the cross section, how this dimension A compares to the wavelength, how the length compares to the wavelength. So if you have a situation where where the wavelength is comparable to this dimension A as well as the dimension L, then you start treating it as a waveguide. So what do you mean by waveguide is you have to consider the full Maxwell's equation. So you have to actually solve for the field in the cross section as well as how that actual mode is propagating in the waveguide, right? So that involves a full electromagnetic solution, and that's usually done using some kind of simulation, like softwares like HFSS, for example. And then you have another special case. So the transmission line is a special case of a waveguide where the wavelength is much longer than the dimension A, but it is still comparable to dimension L. So it still has wave-like properties along the length, but it behaves as lumped along the cross section, right? So that's a transmission line. And then the other case is when the wavelength is very large, meaning your frequency is very low, and the wavelength is much larger than dimension A or dimension L, you can just treat it as a lumped element. So you can just treat it as a single resistor, single capacitor, single inductor, right? So this is the main kind of three different regimes that a link can behave depending on how the wavelength compares to the dimensions, okay? And really it comes down to how the phase, whether the phase is varying along the length or the phase is relatively constant, right? And then, then we talked about another very important concept, which is why does this actually matter? So why is it that the frequency and why is it that signal integrity actually matters? So the link itself basically behaves as some kind of low-pass filter. And so when you're sending a signal with sharp transitions, what's actually happening is the link is kind of filtering out the higher frequency components of the signal. And so in the end, you end up with a signal that's kind of distorted. So the signal can have different kinds of ripples. It can have some shifts both in amplitude because of attenuation in the signal, as well as shifts in the time domain, in the temporal dimension as well, because of the fact that the signal can be delayed, or there could be some random shifts because of something called jitter, right? And so in the end, even though this is your signal, when you receive it at the receiver side, the signal can be completely distorted. And what happens is, say you are sampling the signal at some point, at the transmitter, it's supposed to be a 1, but at the receiver, you could detect it as a 0. So you end up with bit errors, right? So signal integrity is about how you design the link so that you can actually minimize these bit errors as much as possible. And then, we talked about what is a common way to visualize signal integrity. What you do is you take the entire signal. So the signal is basically some stream of ones and zeros in time. But to visualize how that entire stream behaves, what you do is you kind of fold it upon itself. So you divide the entire signal into a bunch of unit intervals, and then you basically overlap all the unit intervals on top of each other. And when you do that, you get something called as an eye diagram, right? So at the transmitter side, because the signal is very sharp, your eye diagram looks something like this. So the eye is completely open. But as the signal propagates through the link, because of the various distortions of the signal, when you construct the same eye diagram, you will notice that the eye essentially closes both in the Y which is basically the amplitude, as well as in the time, which is the x, right? So, so this is typically what happens. For example, if a link wasn't designed properly, if you basically measure if you find out the eye diagram at different points in the signal, initially the eye is completely open, but as you move along, because of signal distortion, the eye starts closing. And usually what happens is you define a threshold, something called as an eye mask. And as long as the eye opening is larger than the eye mask, you say that signal integrity is satisfied, which means you can sufficiently, you can sample the signal accurately at the receiver side, minimizing bit errors. But if it's within the eye mask, then then the ones and zeros get jumbled together and you get too many bit errors. And then you say it has failed signal integrity. So how I didn't mention this last time, but how exactly do you do this in practice? How do you generate the eye diagram in practice? So what you do is once a link is designed, so imagine you had you wanted to test the signal integrity of some link between a transmitter and receiver. So what you do is you send a pseudo-random bit sequence on the transmitter side. So it's just some random bit sequence. And then at the receiver side, you just measure what is the received signal, and then you basically, and all this is done in software. So it takes the received signal and then it constructs the eye diagram for you, so that you can visualize how the signal is distorted at the receiver side. So that's usually how these kind of diagrams are constructed. And there are tools that actually, you just connect. You just connect it at the receiver side, and it gives you the eye diagram, so you can check whether the link is working properly or not. In order to design the link correctly, we need to address several causes of signal degradation. So those are reflections, then there's frequency-dependent attenuation, frequency-dependent time of flight, and then we talked about crosstalk. We haven't yet talked about EMI, EMC. That'll be, I'll discuss that today. These are more related to power integrity, which I think Professor Iyer would have already talked about. And so in this class, I think what I want to do is last time I talked a little bit about transmission lines and how to calculate the characteristic impedance of the line, but I haven't talked about how to actually design a matching network, how to actually do matching in practice. I did talk a little bit about how matching can be done. When you have, for example, a bend in the trace, or when you have a trace transition. But in this class, I want to kind of give you a flavor for how this kind of impedance matching can be done to prevent signal reflections, okay? And I'll talk a little bit about how that can be done using a geometric technique, which is called as Smith charts, okay? I'm sure people in electrical engineering would have heard of Smith charts, but for those of you who are not in electrical, it'll seem completely new. But if you have some basic understanding of math, I'll try to explain as simple as I can. But if you don't understand at any point, you just ask me, okay? So we'll focus on matching as well as how matching can be done in practice. And then we'll also talk about EMI and EMC, okay? And then finally, once I've taught matching and EMI, EMC, I think I will give you like a real world example from my own experience of how you kind of design a trace for signal integrity, okay, for a frequency of around 50 gigahertz. So I'll give that as a kind of a case study to show how it can be done in practice. Yeah, so let's first start with, before we go to matching, because that's a little involved, let's first little bit recap on crosstalk. EMI crosstalk, they are different phenomena, but they're also very similar to each other. It all depends on parasitics. So if you remember, crosstalk is basically how one trace affects the other. So for example, here you can have two aggressors, and the aggressors affect the victim trace because of the fact that there's some kind of coupling between them. And the coupling can be either capacitive or it can be inductive, right? So what happens is, say I'm looking at this trace on the right. When you have some signal fluctuation here, because there's a parasitic capacitance between the aggressor and the victim, a variation in voltage here will cause a corresponding variation in voltage here because of the fact that the capacitance likes to keep the voltage across its terminals constant, okay? So when this, so imagine the signal here, I have that here. Yeah. So imagine this is the aggressor and victim. So imagine the victim was high, so it was at 1. Then what happens is when the aggressor suddenly goes from 0 to 1, because this capacitor likes to keep the voltage across it constant, it will end up pushing this terminal here also high. So what will happen is this terminal goes up. There's a little overshoot, but this overshoot is also transitory, right? So because this coupling really depends on frequency, so it only happens when there's a transition. And then once the aggressor settles, this also settles back to its original value. That's why you see this fluctuation go up and then it kind of decays and comes back down. Okay. So, I'm going to ask you a question. So can anyone tell me what really determines how fast this comes back to 1?
Anybody? Anybody have any analogies of similar phenomenon they've seen before? Yeah, Vikram?
Is it to do with like the how fast the capacitor can discharge, basically?
Yes. Yeah, you're right. It's a function of so basically this line is connected to some driver, right? So it depends on the drive. The driver is the one that's actually pushing this high, right? So it really depends on how fast the driver can bring it back to the original voltage value, right? So this is basically an RC kind of time constant. So it is the RC time constant of the basically the drive strength of the driver as well as the parasitic capacitance along the length of this link. Okay, so this is basically it's an RC kind of a decay here. And so similarly, the opposite side, when this victim is low, and then you have a 0 to 1 transition, it just overshoots high, and then it starts decaying back to 0. Okay, so now this wouldn't be a problem if you can wait an infinite amount of time. But the problem is, as the signals get faster and faster, these transitions happen more often. So, and they also happen very close to each other. So at the receiver side, you're going to have a signal that's going to be very bumpy. And then because you're sampling at a certain period, if the bump doesn't decay fast enough, then you can have a situation where you can detect a 1 as a 0, a 0 as a 1, right? And that leads to bit errors. And so, you can have this, it can be because of this capacitor effect. It can also be because of an inductive effect, which I have not drawn here. And in the inductive effect, what happens is, say the aggressor has, because it's a voltage and current, right? So it's not only a voltage that's there in this line, there's also current that's flowing. So in the inductive case, the change in the fluctuations in the current here induces a fluctuating magnetic field, which in turn induces a fluctuating current here. So in that case, the inductance or the magnetic coupling between the two lines causes the fluctuations in the victim side, and which in turn can cause bit errors. So both capacitor and inductive coupling basically can lead to these kind of bit errors, right? So yes, so actually, let me see. Yeah. So we talked about how we can mitigate coupling. Usually, inductive coupling is not that important because inductive coupling, if you quantitatively see, inductive coupling is usually not that strong for these dimensions compared to capacitive coupling. So usually, capacitive coupling is more important. But some of the common ways to minimize this coupling is when you have this kind of multi-layer stack of metal wires, for example, in a PCB, what you typically do is you try to isolate layers from each other by inserting a blanket sheet of metal, which also serves as a power plane. So, for example, you can have a VDD or ground plane that separates multiple layers from each other. And what this plane does is it's basically acts as a shield. So it shields the field from this side to this side so that you no longer have coupling between them. And also, if you have a situation where two traces have to kind of run one on top of each other, you basically do something called Manhattan routing, wherein the two traces are kind of orthogonal to each other rather than in the same direction. Why you do that is because when they're orthogonal, you minimize the overlap area between these two traces. And if you remember, capacitance is proportional to area. So if you minimize this overlap area, you essentially minimize the capacitive coupling between the two levels of traces, right? So that's how you avoid, you essentially avoid, cross coupling in a multi-level PCB, for example. And then we also talked a little bit about frequency-dependent attenuation and time of flight. This one, I don't want to stress, I don't want to go too much into this because this is more kind of focused more on EM. But the basic kind of idea here is that when you have a transmission line, you have to not only consider the fact that, it's just a one-dimensional line, but it also has some kind of a field distribution in the cross-section. And what happens is that that field distribution in the cross-section usually depends on the frequency, okay? Depending on what is the frequency of a signal, it can have a different field distribution in the cross-section. And because a different field distribution in turn means a different effective dielectric constant in the cross-section, different frequencies actually end up traveling at different speeds, okay? So you get something called as a frequency-dependent time of flight, where, for example, when you have a higher frequency, because in a higher frequency case, the most of the field gets confined within the region with a higher dielectric constant. So your overall effective dielectric constant actually increases, versus when you go to a lower frequency where the field is more uniformly distributed between epsilon naught and epsilon, right? So as you go to higher and higher frequencies, what happens is your effective dielectric constant in the cross section is actually kind of increasing. So the time of flight is actually is increasing as well. Okay. So, and that you can see here is if you compare these three frequencies, frequency 1 is greater than 2, greater than 3, and therefore the effective dielectric constant of 1 is greater than 2, greater than 3. But the speed of the signal is basically speed of light over square root of epsilon, right? Because the speed of light is 1 over square root of mu epsilon, and so from that 1 over square root of mu naught epsilon is speed of light in vacuum c. So from that you get the speed in any material is c over square root of epsilon effective, right? So you see that the signal that has a higher frequency is the one that travels at a lower speed, right? So now you have a situation where each signal component, so you have a digital signal that has several frequency components. So you have a situation where each frequency component is now traveling at a different speed through the same link because of the fact that each frequency component experiences a different effective dielectric constant in the cross section. And also you have, on top of the fact that there's a frequency dependent difference in the speed of the signal, there's also a frequency dependent attenuation of the signal because of something called skin effect, which is as the frequency gets higher and higher, what happens is most of the current tends to be pushed towards the perimeter of the conductor. So the effective cross-sectional area reduces with frequency. So higher frequency signals tend to experience a higher resistance in the link, and therefore they tend to get the link tends to be more lossy for higher frequencies, and the signal tends to decay faster, right? And that's what this looks like. So initially say the signal was here, but as the signal propagates through the link, the signal is losing power, so it's kind of decaying in amplitude, right? And this is also going to be dependent on frequency. So putting all these things together, the frequency-dependent time of flight and frequency-dependent attenuation, you have this situation where, say you started with this kind of bit stream, which can be broken down into a bunch of different frequency components. Each frequency component is traveling at a different speed, so it arrives at a different time. So they're going to be shifted in phase. And also each component is going to be attenuated by different amounts. So then when you add it up, because everything is now shifted in time and shifted in amplitude, you get something that's jumbled up like this, right? And if this eye opening exceeds the eye mask, then this itself can cause signal integrity issues. Okay. So now, again, this is something I didn't talk about last time. How do you mitigate this?
Any suggestions? Anybody? Okay, Gautam, continue. Nobody wants to answer.
Yeah, okay. So one of the first things you need to do is you need to make sure that the substrate's dielectric constant doesn't change with frequency. Second is when you go to higher and higher frequencies, if you see here, this is yeah. I didn't talk about different kinds of waveguides, but this is a microstrip. So in a microstrip, depending on frequency, the effective dielectric constant actually changes with frequency. But imagine you didn't use a microstrip, but you use a strip line, right? So a strip line looks something like this. Uh, so yeah, unfortunately, I wish there was a board that I can show, but a strip line basically has the same dielectric constant on the bottom and the top, with a ground plane on top and bottom. So for that, the dielectric constant tends to be more, the effective dielectric constant tends to be more constant with frequency, right? So those are some ways that you can make sure that the time of flight doesn't change much with frequency, okay? And also, if you see most of the high frequency designs, the conductors are usually made very thin because of the fact that most of the signal is anyway going to propagate to the perimeter. So when you make the conductor very thin, what happens is the effective resistance remains also almost the same with frequency. It does still decay, but not as much. Okay, so those are some ways you can essentially mitigate this. Although not completely, this one is not very this one will there will always be some kind of attenuation with frequency, but then at least the phase difference can be controlled by choosing a different kind of waveguide structure in the cross section. So now let's move on to EMI and EMC, which is electromagnetic interference, and EMC is just electromagnetic compatibility. So, the fundamental principle of EMI is basically Faraday's law of induction, right? So if you guys remember Faraday's law of induction from basic physics, if you had a loop of wire, as you can see here, and say I connected a voltmeter, and I had a magnetic field that is passing through this loop, I would get a voltage. I'll measure a voltage in this loop depending on how fast the magnetic field changes. Okay, and that's expressed by basically this is Faraday's law. Basically, the potential across the loop is going to be related to the time rate of change of magnetic flux through this loop, right? And so essentially, because if you consider a situation where B is time harmonic, that is B is sinusoidal, because you remember we are always trying to see how the different frequency components are being affected. So imagine B is sinusoidal. So then if you just plug that in here, you'll find that B is essentially proportional to frequency, right? So the higher the frequency, the more is the voltage that's going to be induced in your loop of wire, right? So this is also the fundamental principle of electromagnetic induction, okay? EMI, and what EMI actually does is when you have a signal in a line, because of interference from other objects nearby, you can end up adding a kind of high frequency noise to the signal, which can lead to signal integrity issues, okay? So, here's an illustration of what EMI typically looks like. So say you have a transmitter here, you're sending some bit stream, and this is your channel. But remember, a channel is always it has two components, right? So it has to have a forward current path as well as a return current path. So this is a transmitter, it's sending a signal. So the signal goes here, and this is your return path over here. So essentially, this is a loop. And so imagine now you have other things nearby, right? So imagine there's a high frequency antenna, or there's a cell phone, or there's some other link nearby. All of these things are radiating high frequency signals. And as the frequency of these radiated signals increases, what happens is this kind of time varying magnetic field can cause a voltage to be induced in the loop because of Faraday's law of induction, right? So what happens is, say this is Vs of t, is the original voltage that you send. As the voltage travels through the channel, you already know that it's going to be attenuated because of the resistance of the channel. So at the output side, it's going to be the input signal, Vs of t, times some attenuation factor. But now what you've done is, because of all these high frequency kind of things nearby, which are inducing voltage shear through Faraday's law, you're also going to add this noise signal, right? So you also have a high frequency noise, V noise of T, right? And this noise that's induced is directly proportional to frequency because, V is proportional to frequency, right? Because of Faraday's law. So this noise signal increases as the frequency of these different components increases, right? So generally when you have any link, if you keep any high frequency source nearby, the link is essentially going to start picking up that high frequency source, and then it's going to add it as a noise to the signal that's already traveling across the link. And if that noise is, and because the signal is getting degraded as it travels through the channel because of attenuation, if that noise amplitude is comparable to the signal strength over here, then you have a situation where your noise and signal are kind of jumbled together, and you cannot distinguish one from the other, right? So in electrical engineering, that's often referred to as SNR, signal to noise ratio. So if your noise signal is comparable to your signal strength, then you essentially lost information, right? And the amount of noise signal that's picked up is going to be proportional to the frequency of these radiators. Any question?
Yeah, please ask some questions because, I mean, if you don't understand, it's very important. There's no dumb questions here. All right, this is pretty important stuff to understand. I mean, this will help you in your project. So if you have a question, definitely ask. So I know for some people, this is like new material they've never seen before. For some people, it's a review. So. All right, continue.
Yeah. So what are some ways to mitigate this, right? So one of the most common ways to do this is to essentially use a Faraday cage. So imagine this is your link. If I put a metal shell around it, completely cover it, then any outside signal is just going to reflect back, right? So it's not going to affect this link. And this is usually done in practice. Sometimes a direct, you just put a metal shell on top of your high frequency components to shield it from everything outside. And this phenomenon is also called shielding. Okay, so essentially what you're doing is you're putting a reflector around the whole thing so that any signal just gets reflected back and doesn't get picked up by the link. Sometimes it's also difficult to put this entire cage around the link. So what you can also do is you can also do this two-dimensionally. So for example, if you have a PCB with a multi-level stack, you can essentially put metal planes on either side. And these metal planes also do the same thing. So they act as a Faraday cage. They kind of shield the outside, right? And if you remember, if you guys remember a little bit about a Faraday cage need not be continuous. So it need not be a direct shell of metal. It can also be a cage of metal. It still behaves the same way, right? So what you can do is rather than having this full shell of metal, you can have two ground planes. And if I just connect the two ground planes by array of vias on either side, in the PCB, then essentially I've created a cage that encloses the metal wires, right? And I prevent any EMI from being picked up. So that is shielding. If you guys know, seen in a lot of the power cords, you will see this kind of cylindrical object that's on the power cord. What this is actually a ferrite core. It's called a ferrite core damper. And what it does is, it's basically a magnetic material that's kind of wrapped around this core. Sorry, that's kind of wrapped around the wire. And then let's say the wire, this wire is carrying your signal as well as the noise that has been picked up because of EMI. Then what happens is because a time varying current generates a magnetic field, and the magnetic field in turn induces eddy currents in this core. And the eddy current really depends on the frequency. What happens is the higher frequency signals induce a higher eddy current, and it creates more loss in the magnetic material. So the higher frequency signal tends to be attenuated more in this material, right? So this essentially behaves like a lossy filter. So it kind of filters out higher frequency components by essentially converting the energy to heat in this material. And then at the end of it, you just get the lower frequency components, which is your signal, Vs of t. Does this make sense?
Why would we want that for a power cable? Does anyone know?
We don't wanna have spikes that could damage the chip.
Yeah, exactly. You don't want that high frequency noise causing some kind of stray, um, you know, part on top, so, yeah. Yeah,
Sorry, what does the Barrett core do to the noise signal portion of the signal impedance?
See, okay, so the noise signal, right? V noise is proportional to frequency, right? So the higher the frequency of the whatever things are surrounding it, the higher the frequency of the noise signal, right? So what the Farad core does is when your signal is passing through this line, the signal is going to generate a magnetic field, right? That magnetic field is existing everywhere. But where the ferrite core exists, that magnetic field, because there's this magnetic material here, that magnetic field is going to essentially induce eddy currents in the material, right? You know what eddy currents are, right? Whoever asked that question, do you know what eddy currents are?
eddy current.
No.
I see. So eddy current, it's basically the same as this, okay? So it's the same phenomena as this, but it's a reverse. It's kind of like the reverse. It's the same. Sorry, it's not the reverse. It's the same phenomena. But in eddy currents, what you have is rather than having a loop of wire like this, you imagine you had a plate of metal, right? So imagine I had a plate of metal here, and then I was passing time varying magnetic field through it. Then that time varying magnetic field is going to induce a current that's going to flow in that plate of metal, and so that current is going to induce heat in the metal, right? So imagine I had some source that was actually creating this time varying magnetic field. What ends up happening is that current induced in the metal plate is going to heat up. So that ends up consuming the power of whatever source was generating the field. Does that make sense?
Thank you.
Yeah. So it's the same thing here. What you're actually doing is because the noise signal is going to be high frequency, and because the eddy current induced here is proportional to frequency, the higher frequency signals are going to generate a higher eddy current, which is going to create a higher heating in this material, which means more of that noise signal is going to get damped out because its power is being converted to heat in the material, right? So what this ends up doing is it ends up essentially attenuating the higher frequency noise signals, and then only the lower frequency signals get to cross. So by designing what is the thickness of this ferrite core as well as the length of this ferrite core, you can control how much of the noise is removed and how much of the signal is being passed. So that's dampers. And then, you always also have error correction. Again, this is a very complex topic, so I'm not gonna really go into this. But sometimes what happens is even doing all these things, you're still going to get bit errors. But what you can do is you can do a trick. The trick is that you can add more kind of redundant bits, and then you can do something in the software domain to correct errors. So even if you had a bit error, you can always detect the error and then correct it. Okay, so that's called error correction. But this is goes more into information theory, so I'm not gonna really go into that. Okay, but there are many ways you can mitigate these kind of the EMI issues. Yeah, so before we get to case study, I think I'll go back to matching. But also if you look at here's some examples of different kinds of designs that are done at high frequency. So I'm going to ask a question here again. Can anyone tell me why these traces here are kind of squiggly like this?
Anybody? The analogy could also be like something with like roads, right? You had to reach the same point the same amount of time. Anybody can make an analogy why that would be important if you're, I don't know, trying to make some analogy here. Or can somebody come up with an analogy for this? Why we'd want a squiggly line?
This is same.
Yeah,
To keep the distance same probably. Because
Yeah, you're right. Yes. So when you have like many links, right? So imagine you had a chip, again, a chip is not shown here, but imagine you had two chips here and you had many terminals here connecting to many terminals here, right? Typically, you want to do something called phase matching. So you want every signal from every terminal to arrive at the other terminal on the other chip at the same time, right? Which essentially translates to each wire being the same length, okay? So the thing is, a lot of these softwares, like this is, for example, Alton is a common PCB design software. What it does is it does it automatically for you, right? And it finds out what is the optimal kind of wire design. So it's an optimization problem. We're minimizing the length of every wire, but at the same time keeping the length of every wire the same, right? And when you do that, this is one of the solutions where although it looks completely random, this is the best possible situation where you have every wire being minimal length possible while also maintaining the same length between all wires. And also, if you notice here, it's not very clear here, but you see these kind of cuts everywhere. These are the meters, right? So remember that whenever you have this kind of a bend in the wire, you don't want to have a sharp 90-degree bend. You want to do that kind of periscoping kind of cut. So that's why you see that all these wires have this kind of 45-degree cut, which is basically the metering or the chamfering, right? So this is a typical high frequency PCB. When you go to even higher frequencies, so these high frequency PCBs are, typically, I think, tens of gigahertz. But when you go to even higher, like 100 gigahertz, 200 gigahertz, and so on, the design completely changes where even something like this is bad because even this can cause radiation. So in very high frequency packages like 200, 100, 200 gigahertz plus, or even 50 gigahertz plus, what you do is you cannot have very sharp changes. So if you see here, all the lines are varying very gradually, right? So this is called an adiabatic kind of a structure. So everything kind of varies gradually to minimize reflections. And, I'll talk about a case study where, I show, from my own experience, how you design a link like this. But before we get to that, I think I want to go back to, transmission lines and matching. Hey, Vineet, can we take a quick break since that topic is going to take time?
Take a break, yeah, take a 5 to 10 minute break, yeah.
Yeah. Reflections in the time domain. And then I'm going to switch to basically a kind of way to understand how matching can be done using actually a technique called Smith chart. But that part I would say is more like a bonus lecture. Just try to understand and ask me questions. But if you don't fully get it, don't be too worried because that's not really the point of the packaging class. But as long as you understand the fundamentals of signal integrity, that's more than enough. Okay. So let's first recap a little bit on on transmission lines, reflections, and matching. So remember that you have the transmitter, link, and receiver, and so you can do a trick. The trick is that even though you have a signal here at high frequency and your phase is changing along the length, you can always divide the link into a bunch of differential elements, and within each differential element, the phase is almost constant, right? So just like in you essentially do the calculus trick, wherein within each differential element, everything remains constant. So within an element, because the phase is constant, you can use a lump model, right? So this entire link can be broken down to a bunch of differential elements here, where each differential element has this RLGC kind of lumped model. And the reason it has RLGC is because it can always have a resistance, inductance, and it can also have these parasitic capacitance, and G is actually a conductance, right? So imagine, for example, the insulator separating the metal and ground is lossy. It was passing some current through it, then that will be modeled by this G. Okay, that's why you have all four components, right? So once you do this, you have this piecewise kind of a lumped model. Then what you can do is you can take any single element, say at a location Z. So at any location, we are assuming that the transmission line is of length 0 to L along the Z direction. Okay, so I'm assuming everything is along the Z axis. So if I take any location Z, and that particular element at that location Z, which has a length of delta Z, let's say is this one, then the voltage at one side can be modeled as, can be written as V of Z, and on the other side is V of Z plus delta Z. And similarly, the current at this side is I of Z, and the current at this side is I of Z plus delta Z, okay? Then you can simply use Kirchhoff's voltage law and current law. So for example, V of Z plus delta Z, which is the voltage here, is just going to be this voltage minus I times this impedance, right? So V of Z plus delta Z is V of Z minus I of Z times this impedance. Similarly, what is the current I of Z plus delta Z? It's going to be this current, the current I of Z minus the current that is drawn by this parallel components, right? So that's what I've written here. So I of Z plus delta Z is I of Z minus this voltage divided by these impedances, right? And so if you do all this and then you rearrange, and then remember that this this model works when delta Z tends to 0, limit delta Z tends to 0. So that is going to the continuum model, which works for any frequency. So when you take limit delta Z tends to 0, these equations essentially become differential equations, right? So you get a dV of Z by dZ that depends on I of Z, and di of Z by dZ that depends on V of Z, which is essentially telling you that there's a kind of a wave of voltage and current that is propagating along the transmission line. So then you can make each of these equations dependent only on one. So for example, if I differentiate this again and then substitute the di of Z by dZ over here into this, then I will essentially get two second order differential equations that only depend individually on voltage and current, okay? And these are wave equations. And why are these wave equations? Because, if say, this thing is just a constant. So let's say you can assume this thing as some constant gamma square. And so if you substitute that and then you find the general solution, this would be the general solution for these equations. And if you notice that these equations are essentially representing two waves, one that's propagating along plus Z and one that's propagating along minus Z, okay? And this constant gamma is a complex number. And why that is important is because gamma being complex means that I can write gamma as, say, some alpha plus j beta. So then the real part of this gamma basically represents the loss along the line, because if, say, gamma is the real part, say alpha, then I would have a term that's e power minus alpha z, right? Which means that the signal is decaying exponentially along the length of the line. And the imaginary part represents the actual propagation of the wave, right? So this is representing a wave solution, taking into account both the attenuation of the wave as well as the propagation of the wave along the line. Everyone clear with this? Okay. Similarly, you can get an expression for I of Z as well. But you can always, because I and V are related by this equation over here, if you know I of Z, you can find V of Z, and you can represent I in terms of components of V. So if you do that, then you can get an expression for I of Z in terms of the parameters of V of Z, right? V naught plus and V naught minus. And when you do this, you will get a constant, and this constant has the units of impedance. And this is often called as a characteristic impedance, because if you see, all these parameters are essentially constants that depend on the transmission line. So it is a characteristic of the transmission line, okay? And so now that you have an expression for the voltage and current at any point along the line, you can calculate the impedance, which is just defined as V by I. So the impedance at any point of the line is just V over I, which is given by this expression, okay? And usually in convention, what you do is you assume that the receiver side is at Z equals 0. And then the transmission line is actually starting from minus L, okay? So the transmission line, remember, is length L. So it's going from minus L to 0, 0 being the receiver side, okay? And so if you remember, since this is the expression, and if you substitute at this location Z equals 0 into this expression, then you get something like this. But at the same location, Z equals 0, the impedance is also ZL, right? So ZL is equal to this. And then when you rearrange everything, you essentially can get an expression for the reflection coefficient, which is ZL minus Z0 by ZL plus Z0, okay? where the reflection coefficient is just defined as the ratio of the amplitude of the reflected wave by the amplitude of the incident wave. Okay. And so what this expression is really telling you is that if the impedance ZL is the same as the characteristic impedance of your transmission line, then your V naught minus is 0, which means there is no reflected wave. So all the wave that is transmitted along the transmission line goes to the receiver. On the other hand, if ZL and Z naught are mismatched, say they are not equal to each other, then the reflection coefficient is non-zero, which means you have a reflected wave. So what's actually happening is the incident wave is coming to the receiver, but not all the incident power is going to the receiver. Some amount of the incident power is actually reflecting back towards the transmitter. Okay, and so if you have a situation where that reflection is too large, then what can happen is most of your signal gets reflected back and very less signal actually goes to your receiver side, right? And so what does that mean? That means that at the receiver side, your eye is starting to close because your signal strength is reducing because of the reflection, right? This is a very important concept. Everyone understands this, right? And you can always go back, do the derivation yourself and convince yourself that this is what reflection coefficient is.
I have a question for the class. Does a lossless transmission line still have an impedance? All right, can someone explain why? What does it mean by lossless? Yeah,
Well, it can be lossless, but it still has an impedance because that just describes the ratio of voltage to current on a line.
sure.
Yeah, that's correct. Yes.
Everyone understands that? All right, I think we're good.
Okay. And this formula is also very universal, so it doesn't only apply to transmission lines. In fact, it applies to any kind of wave phenomena. Okay, like for example, it even applies to sound waves. So if you had, a situation where on one side you had water and the other side you had, say, oil, for example, and you're passing sound waves, then the sound wave will reflect by the same expression, but the Z's will be replaced by viscosity. So the analog in fluids of impedance is viscosity. The analog for impedance in optics is refractive index. Okay, but the mathematics is very similar because the wave equation applies for any kind of a situation, right? So really, what really changes in this expression is Z. So you have analog of Z depending on what kind of phenomena it is, right? Yes. And so, this is just kind of understanding more about what this expression means. So remember, gamma, the reflection coefficient is ZL minus Z0 by ZL plus Z0. So imagine now ZL was a short, right? Imagine I just shorted this wire to ground. Then in that case, what is ZL? ZL is 0, right? So if I substitute ZL as 0, what do I get here? I get gamma as -1, right? So if gamma is -1, what does that mean? V naught minus is now equal to minus V naught plus, right? That means all the wave that is incident gets reflected back because the amplitude of the reflected wave is same as the incident wave, right? So all the wave is reflected back if ZL is shorted. Now imagine what happens if ZL was open, right? So also, even though the voltage gets reflected back, the current actually gets reflected back with a 180-degree phase shift and the current is 0. So you can actually see this. Yeah, so these are different, for example, conditions of this expression. So if it's perfectly matched, ZL equals Z0, reflection coefficient is 0, and there's no reflected wave. So V naught minus is 0. If you have an infinite load impedance, right, which means this is basically an open, which means it's infinite. And then when you substitute ZL equals infinite into this expression, you get gamma equals 1, right? Which means V naught minus is V naught plus. So all the voltage is reflected back. And also it is in phase with the incident voltage. And also if you calculate the current, which is just going to be, minus gamma V naught plus by Z naught, which you can get from the previous expressions, then you get the current as minus V naught plus by Z naught, which means all the current is reflected, but it is out of phase by 180 degree. okay, if you have infinite load impedance. Similarly, if you had zero load impedance, then you have a short circuit situation, and then you can see here that all of the voltage is reflected, but the voltage is reflected 180-degree out of phase, while here it is in phase, which makes sense because at the output side, the voltage, if the output was shorted, the voltage has to be zero, right? So the reflected wave has to be 180-degree out of phase so that when you add them together, they end up being zero, right? Because the voltage for a short must be zero, right? So the voltage is out of phase by 180, but the current is reflected in phase, right? So what this is telling you is that if the output was open, then the voltage is reflected completely back in phase, and the current is out of phase, so the current at the output is zero. Similarly, if the output was shorted, the voltage is reflected out of phase, so the voltage at the output is zero, but the current adds up, which makes sense because if it was shorted, you'll have a very high current, right? Does that make sense? Again, the best way to really understand this is to go back yourself and step by step do the derivation and convince yourself that that is the case. Okay. So all the steps are here. That's why I have included all the steps of the calculation so that you can do this yourself and convince yourself that that is the case. When I present this, it's often quite difficult to see why that is the situation, but if you go back and work it out, you'll find that that is the case. And so, what you have learned so far is that when you have a wave that's traveling to the right, say V naught plus, depending on what the ZL is, you have a reflected wave, which is gamma times V naught plus, and you have a transmitted wave, which is T times V naught plus, right? Because if all the portion is not reflected, then the remaining portion must be transmitted, right? So what you can do is, in order to find T, you can also calculate, you already have an expression for gamma, but you can also calculate what T is by doing the simple thing, which is that, remember at any location Z, along the Z-axis, KVL, KCL applies, right? At a given point, KVL, KCL always applies. So if I take at location Z equals 0, I use KVL and KCL, then I can essentially say that, V naught plus gamma V naught plus is equal to T V naught plus, right? Because the voltages must add up. And similarly, you can do current continuity also. And then if you rearrange, you can get an expression for transmission coefficient as this, okay? And also you find a relation between T and gamma. So 1 plus gamma is T, which is essentially energy conservation, okay? So what this is telling you is that, if you add the incident wave plus the reflected wave, the incident wave must be equal to the reflected wave plus the transmitted wave, right? Which means that, the power has to be distributed, right? So it's an energy conservation. Okay, after this, it gets a little kind of complicated, but, everyone understands up to this point. Main thing to understand is that there's an incident wave. If there's a mismatch in impedance, some gets reflected, some gets transmitted, okay? And the amount that gets reflected is gamma V naught plus. The amount that gets transmitted is T V naught plus, okay? So now we're going to consider a little complex situation wherein, let's say you have, at the source side, you have some, basically this is a source, and you have some source impedance here, ZS, because remember, the transmitter can also be modeled by its Thevenin equivalent, right? So you can have a voltage source, some impedance ZS, and then you have transmission line, some impedance ZL, right? So now imagine a general situation where nothing is matched, right? So the Z naught is not matched to ZL, it's also not matched to ZS, right? So now what's going to happen is every time the signal goes to one of these endpoints, it's going to get reflected and going to get transmitted, right? Because there's going to be a reflection coefficient at each endpoint, right? So imagine now I'm sending a wave. So the wave, let's see if I can potentially draw this. Okay. I'm going to represent the wave by a box, okay? Okay. So imagine this is the wave, okay? So the wave, so initially when I switch on the circuit, the wave is going to propagate like this. But the moment it hits this terminal here, because the impedances are mismatched, some of it is going to be reflected back, some of it is going to be transmitted, right? So the sum of it that is reflected back then has to travel all the way back. And then once it reaches here, again, there's a mismatch in impedance. So some of it is transmitted to the source, some of it is reflected again. So this thing keeps bouncing back and forth like this. And every time it hits the endpoint, some of it gets transmitted, some of it gets reflected, okay? So to simplify this, let's say this was a step function, right? Let's say this at time t equals 0, let's say the voltage goes from 0 to some value v, right? So what is some value Vn of 0, right? So this Vn is going to, and the time it takes for this to travel all the way here is essentially the time of flight, right? So that's going to be the speed of light over the square root of the effective dielectric constant of the transmission line in its cross section, which we already talked about, right? So if you plot this in this is often called a space-time diagram because it shows you both in space and time how the signal is propagating. But you can see that the signal is traveling in time and in space. And then here some is getting transmitted, some is getting reflected, and it keeps bouncing back and forth like this, right? And this keeps going on to infinity. But every time it keeps going, the signal is slowly building up. So now let's add some expressions here. So Vn of 0 is the original signal here. So that's going to travel all the way here. But as the signal travels, it's obviously going to pick up a phase, right? Because remember, when a wave propagates, the phase that it picks up is e power jkx minus omega t, right? So as it travels along a certain length, it picks up a phase. So let's say it picks up a phase e power minus j theta, right? So Vn of 0 goes all the way here, it picks up a phase, and then some amount is reflected, some amount is transmitted, right? So the reflected amount is going to be gamma at the receiver side times this voltage, and the transmitted is going to be this, right? And so now the reflected wave is now going to go all the way back, and then it's going to be transmitted and reflected. And so you take this expression here now and multiply it by Ts, which is at the source side, to get the amount transmitted, and gamma S to find the amount that's reflected, right? And then you keep doing this, and it gets more and more complicated because it's undergoing more reflections, right? So for example, let's take this expression. So what this is telling you is this was the original signal. It had already undergone one reflection at the receiver side, one reflection at the source side, then again one reflection at the receiver side, right? So as you keep going down, you're going to add more and more gammas, right? Also, I don't know how much you guys like to think mathematically, but the more reflections you have, the more gammas you're adding. But remember, gamma is a number less than 1, right? That means if you consider this as an infinite series, the coefficient is actually, since the coefficient is some power of some number that's less than 1, it's going to eventually converge, right? Does that make sense? Okay. So if I was to see, right, if I was to measure what is the signal at, say, some random location, let's say that location is at z equals L by 4, right? 1/4 of the length. What is it going to look like? So remember, the total time it takes for it to travel this entire distance is TF, time of flight. Let's say that time of flight is, I'm just representing it by capital T, right? So the time it takes to reach here is going to be what? T by 4. So the time it takes to go here is T by 4. And then the time it takes to go here is T, right? And so let's see. So what I'm essentially doing here is I'm seeing how the signal is building up in time, right? So initially there's no signal. Why? Because remember, the receiver already started at time t equals 0, but the signal has not reached here yet, right? So at time t equals 0, there's no signal. But then once I reach t by 4, this signal Vn has reached here, right? So this signal suddenly jumps to Vn, okay? And then what happens? Then this Vn goes all the way here and bounces back and comes back here, right? So now what happens is, so it goes all the way here, bounces back here, but when it reaches here, it's going to add on top of the Vn that was already there, right? So then it's going to be, the signal here is going to be Vn of 0 plus gamma L Vn of 0 e power minus j theta, right? And then once it goes here, reflects back, it's going to be this plus this and so on, right? So what ends up happening is the signal kind of at every one of these instances, you can see these instances are exactly the time it takes for the signal to go to bounce at different locations and reach there, okay? So this is t by 4. Then to go here and come back, what it would be, right? It would be 3t by 4 plus 3t by 4, right? So it will be 6t by 4 plus t by 4. That's why it's 7t by 4. I really want to understand this. This is very difficult to explain on Zoom, okay?
The part I'm losing you a bit. Earlier made more sense.
Yeah, unfortunately, teaching this in Zoom is like incredibly difficult. Uh, See, I think there's a wave, right? There's a wave that's propagating here, and then it's going here, reflecting, coming back. And whatever wave is coming back is going to interfere with this wave, right? Then it's going to go here, bounce back, again interfere. Go here, bounce back, again interfere, and so on, right? So the signal that reached here initially was Vn, and then that signal is now there. But then when the signal goes here, bounces back, that Vn, since it's already there, now gets added with this reflected signal, which is this. And then it gets further added at this time with the further reflected signal here, and so on. Okay. So
Basically, each time it's getting reflected, it's kind of modifying the returning wave, right? That's then getting reflected again from the other end, and so on and so forth, right? You're just basically tracking how this changes, right? The Vn over time. That's essentially what you're doing. You're stepping through it after multiple, different
yeah,
phases and
yeah.
you're doing.
So that's why, so for example, see, the time it takes for this Vn to originally arrive here is t by 4, right? That's why till t by 4, you don't see anything. And then at t by 4, it goes to Vn of 0, right? Because that Vn of 0 has reached here. Now that location is at Vn of 0, but then if you see the time it takes for the signal to come back here, what is this time, right? So this time is going to be, this whole thing is t, this is t by 4. So this is 3t by 4. So this time is going to be what? 3t by 4 plus 3t by 4, right? Which is 6t by 4. So, but from the original t equals 0, that's going to be 7t by 4 because there's already a t by 4 here, right? So that's why you see now at 7t by 4, it's now Vn of 0 plus the reflected wave at the receiver side now being added to it, right? And then now if you, yeah. So now it's a 7t by 4, but then the next time the signal is going to change is when? This has to go here and come back, right? So that's going to be 7t by 4 plus 2 times t by 4, right? So it's going to be 9t by 4. So 9t by 4, you again see the signal increase, right? But you see that these increases are getting smaller and smaller, right? That's because the signal is being reflected, and every time it's reflected, only a certain portion is being reflected back, right? So this essentially is settling towards something. So if you, this is an infinite series, so every time there's a reflection, you're adding more coefficients, but because each coefficient is less than 1, it's essentially tending towards 0, right? So if you add all the coefficients, you'll see that this signal finally settles somewhere.
Sorry. Sorry, quick question. For the why do we add the reflected signal? Is it constructive instead of destructive covariance?
Oh no, there's also phase that's added. See, there's an e power minus j theta also that's added. You have to consider you have to consider the phase also. You are right. Yes. You also have to consider the phase. Yes.
Your ZL can have an imaginary component, right? So just remember. So when you find your reflection coefficient, it's actually, that's very big.
You can go back and think about this. But I would say if you're not following, right, the main concept to understand here is that these reflections are going to keep adding, or depending on phase, even subtractive. It really depends on the calculated phase, right? But in this situation, they're kind of adding up. So although the original signal was only Vn of 0, you're ending up a situation where the total signal is actually higher than what you would expect. So sometimes if this goes very high, then what happens, it can actually damage your receiver or your transmitter, okay? So that's why you also want to make sure everything is matched. Because if everything is matched, then you have a situation where you can essentially avoid this reflection and you can avoid the signal buildup that can happen.
Sorry, sir, can you explain again why we don't want this match to happen?
Yeah, so the signal, okay, the transmitter was supposed to send Vin of 0, right? That's the value of the signal it's supposed to send. That is the signal that's supposed to go to the receiver, for example, right? But now, because of the signal buildup, the final signal in the transmission line is now going much higher than Vn of 0 because of this constructive interference.
To be clear? If not, you can, yeah. Fine.
Do we care what time it stops reflect?
I didn't hear that question.
Yeah. Do we care what time it stops reflecting?
No, it keeps going on forever. It's just, but it's an infinite series, right? So I have only shown up to this point, but you see the step height gets smaller and smaller, right? Eventually, it's going to settle down. See, because the impedance is not matched, right? So some amount of signal always gets reflected. So it's going to reflect, 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 keep reflecting forever, right? But every time that there's a reflected wave, the reflected wave is getting weaker. So, it's going to eventually settle down. See, imagine the reflection is 50%, right? So initially you send 100% of the signal, then the reflected signal is 50% of the strength. The next time it's reflected, it's 25%. Next time it's reflected, it's 12.5%, and so on and so on and so on. And eventually it just goes to 0, right? But it goes to 0 at infinity because it's essentially 1/2 power how many times it's reflected.
Played like air hockey. You hit the side of the puck into the side and it hits the side. Eventually, if they keep oscillating between the two, it's eventually gonna keep losing energy to some point where it just kind of the same concept. It'll level out at the same thing eventually. Right? It won't keep adding, but then the problem is that it's not matched from the beginning. You don't want that initial step increments that are consistently happening. Ideally, you want it to be the same all the way through, right?
Yeah, but in reality is not ideal, so like, do we measure? Like,
No, you can figure out ways to, well, he's gonna cover this, right? You're gonna talk about how to solve this problem, right? The matching network, right? Gautam.
Yeah. Yes. I explained a little bit about how it can be done. Like for example, like yeah. So these are some examples of how it can be done. For example, here, this is a situation where you're going to get some reflections at this 90-degree bend, but then to prevent this reflection, what do? You can do chamfering. You can make a gradual transition, right? So if you do either of these techniques, you can minimize the wave that's reflected back, for example. And then, imagine you had a situation where you had a sudden change in the width. So imagine this is a trace and this is a pad, right? So there's a pad where, say, a wire bond is there, right? So wherever there's going to be a trace connected to a pad that's essentially bigger than the trace, you're going to have reflections. So what do? You don't make a pad like this. You make a pad that's more gradual like this, right? So you can see a real world example of that. You see here how in this case, yes, it's like 90-degree, but you see how in this case, like it's a gradual transition to this, right? It's not a 90-degree bend down.
Hey, Gautam, are you gonna cover like lumped element as well? like physically putting a device like a capacitor or resistor, you're gonna cover that too, right?
Yeah, I am gonna cover that, but yeah, that's gonna take some explanation. Yeah. So there are other ways to match it as well, which I'll talk about later, like in the next slides. But so if say ZL is mismatched to Z naught, you can make ZL match to Z naught by just adding some lumped element here. So for example, you can add a capacitor in series, or you can add an inductor in parallel, or something like that. And when you do that, the net effective impedance here gets matched, essentially becomes equal to Z naught, so that then you would avoid reflections. So that's another way you can actually prevent the reflections from happening. So, so let's go back to this figure, right? So incident wave, reflected wave, transmitted wave. You can also, one of the common metrics that is used to check whether a line, is used when you talk about lines being matched or not, is something called insertion loss and return loss, okay? Which is basically just a way of representing the same thing, but using power, okay? Rather than using voltages, you use power. So if this is the incident voltage, what is the incident power, right? So power is going to be V times I. But remember, the power here is a complex power, right? Because it has a real part and imaginary part. Because the voltage and current are also complex numbers, right? But the real power is going to be what? This expression, it's a very common expression in electrical engineering. If you go read about complex power, you'll understand why this is the case. But real power is V times I complex conjugate real part, okay? So if you look at what is the incident real power, that's going to be, this is the incident wave times the incident current complex conjugate, right? And similarly, you can calculate what is the power of the real power of reflected wave and transmitted wave, right? And then you get expressions like this. And what you do is you define something. So you get expressions like this, and what it is telling you is that, let's say Pi is the incident power, PR is the reflected power, PT is the transmitted power, right? So you have expressions for those. And then you define return loss as the log of the reflected power by incident power. So what you're doing is you're basically representing the ratio of powers with a log, because sometimes what happens is that the amount of power that's reflected back is so small, right? It could be like maybe like 0.001% of the incident power, that it makes more sense to use a log, because in log it's more, you can cover a wider range, right? So you define return loss, and as the name suggests, it's return, which means reflected. So you define return loss as log to the base 10 of the reflected power by the incident power, and the insertion loss as log to the base 10 of transmitted power by incident power. Okay. So imagine you have a situation where you have no reflection, right? So you have perfect matching, ZL equals Z naught, no reflection. So what does that mean? That means that the reflected power is zero, right? So if the reflected power is zero, what happens to the return loss? What is log of zero? What's log of zero?
Infinity.
Yeah, it's minus infinity. Yeah, so it goes to minus infinity dB, right? But usually reflective power is never zero. It's some very small number. So, but however, because, when you put in a log scale, it's going to be some number like minus 60 dB, minus 40 dB, something like that, right? So generally, when your return loss is lower than minus 15 dB or something like that, you say the line is matched. So that's usually a common metric that people use. So if your return loss is less than minus 15 dB, say it's minus 20, minus 30 dB, you say that the line is matched, right? Similarly, if you look at the insertion loss, if you have a situation where there's no reflection, then what happens? The transmitted power is equal to incident power. Then you have log of 1. What is log of 1? Sorry?
Zero.
It's 0 dB. Yeah, it's 0. So the best case scenario for insertion loss is to have 0 dB. The best case scenario for return loss is to have minus infinity dB, right? But it cannot be minus infinity, because you will always have some reflection. So it'll be some very low number, like minus 40 dB or something. So, sorry?
You're right, it's never perfect, right? It's true, it's never perfect, but you can get something less than the threshold you said, right? Minus 15 dB, and you consider that to be relatively well matched, right?
Yeah. So what does that look? And I think, this gives you a flavor for if any of you guys are doing this in the future, you'll use a software called HFSS. And usually when you do HFSS will show you the insertion loss and return loss, right? So I've shown two examples here. So in the first example, the insertion loss looks something like this. So at low frequency, it's around 0 dB, but as the frequency increases, it's kind of sloping down like this. And the return loss is like lower than minus 10 dB. Okay. So this is a situation where there's good matching. So there's good matching because the return loss is lower than minus 10 dB. So it's pretty matched. There's very less reflection. Oh, incidentally, right? What does minus 10 dB correspond to in terms of how much reflection do you have in percentage to get minus 10 dB?
%10.
Yeah, I think you're right. Yeah, I think it's 10%. Yeah. So 90% transmission, 10% reflection corresponds to 10 dB. Okay. And 20 dB is like 99%. So because it's a log scale, right? So by the time you reach 30 dB, it's like negligible reflection, right? So usually people say minus 10 dB is, it depends on the design, but typically minus 20, minus 15 is good enough. Okay. And you see insertion loss very close to 0 dB, which means most of it is transmitted. But generally, as you go to higher frequency, reflections increase. So that's why you see some degree of lower insertion loss as you go to higher frequency, right? So this is a match situation. Can anyone tell? Oh, I have that here. Okay. Yeah. So this is a band pass situation. Okay. So here you see that if you look at the return loss is higher than minus 10 dB for most of the frequency, which means it's reflecting. But when it's very close to this frequency F naught, you see suddenly it's dropping below minus 10 dB, which means it's matched for this frequency. But for other frequencies outside of the range, it is unmatched. Okay. Which means this is a kind of a line which is allowing only a certain band of frequencies to pass, but all other frequencies outside that band is being reflected. So it's a band pass filter, essentially. Okay. So this is, for example, how that would look like in a band pass case. And similarly, you can see insertion loss. You have very low insertion loss for any frequency outside this range, which means there's no transmission. There's no, most of it is being reflected. But then when you reach close to F naught, your insertion loss is going to 0 dB, right? Which means most of it is being transmitted versus reflected. Everyone clear on this? Okay. And like before I get to I'll call it the bonus lecture because last time I thought it wasn't the most popular thing I thought because it was too complicated. So I'll teach that at the very end if there's time. And I'll skip to the very last part and then I'll come back to the Smith chart. But basically, there are other ways to match also, right? So we talked about one way to match is to have gradual transitions in your traces, or if you have a bend, rather than having a 90 degree, doing a metering or doing a gradual kind of curved bend, right? So other ways is to have a lumped element, so adding a capacitor inductor, right? So I think that pretty much concludes what I want you guys to understand from this whole, set of slides as to how matching is done, what reflections are, and so on. And we'll come back to Smith chart if we have time in the end. But I want to skip to, for example, a real world situation, right? So for example, designing, so this is something that I did a long time back, is designing fan out wires on a ceramic PCB for a photonics package. Okay, so this is the photonics package. So this thing here is actually a photonic IC, so it's a PIC. And then these two things are actually fiber optic connections. So you have fiber optics on either side. And then what you do is this is a modulator. So you have optical signal in, optical signal out, but the optical signal is actually being modulated by this RF signal. Okay, so the RF signal is the one that's modulating the light. Okay, and then on this side you have a DC PCB because you need to provide power to the various devices on this. So you have a DC side and you have an RF side. Okay, but the frequency here is very high. In fact, it operates at more than 50 gigs. So if you notice here, the challenge here was how can I design 4 lines where all 4 lines have the same length and all 4 lines are matched, but not only matched at one frequency, they are matched broadband. So they have to be matched all the way from 0 all the way to like 100 gigahertz. Okay. And you look at, how that was done. So one of the ways that, like a way that I did this was I divided this problem into a bunch of parts. So uh, the pitch here, right? So the pitch on the pick is much smaller than the pitch on the SMA. So these are called SMA connectors. They are basically a coax connector. So there's a coax cable that comes here, and then it sends a signal here, right? So the pitch here is very small. The pitch here is very large. So the first thing is, how can I take the large pitch here and kind of reduce it to the small pitch here, which means I need some kind of taper along this length, right? The second thing is I need to kind of curve these lines because I need to make sure that the lengths are the same, right? If I just do straight lines all the way here, each line is going to be, these 2 lines are going to be shorter than these 2 lines, right? So I need to curve them so that I can make the lengths the same. But at the same time, when I curve them, I need to curve them in such a way that if I don't curve them, if I curve them at a very sharp radius of curvature, then the signal is going to radiate out, right? So I need to curve it gradually. I need to taper it. And at the same time, I need to make sure the lengths are the same, right? So that's the challenge here. So how I did this, I divide the problem into like, first, I have this, on one side, I have this wide, basically a wide pitch. The other side, I have this much narrower waveguide. So I first designed the taper, okay? So this is like, I tried different lengths of taper, and typically if your taper length is around 10 times the wavelength, you get a good matching, okay? So, yeah, actually I think this was a video. No, okay. Yeah, so this was a taper, and you see how the signal is coming and the signal is kind of being compressed down to this new waveguide. And because the taper is gradual, you don't get much reflections or much radiation, okay? And this is what I talked about before. You can see this is the return loss, this is the insertion loss. So you see how the return loss is less than minus 20 dB, right? Which means it is matched. But now I'm going to ask the question, which is, why is there these bumps over here? Why is it not just one continuous straight line? So that's one question. And then the other, you see insertion loss is like, it's close to 0 dB, but there is going to be some insertion loss because there is going to be some reflection, right? So can anyone tell me why there are bumps over here?
I guess when they reflected, some of the frequency got constructively interfered, some are destructively interfered.
Yes, exactly. Yeah. Nice. Yeah. So these bumps correspond to when these wavelengths, these frequencies, and corresponding wavelength are actually being multiples of this length, right? So when the frequency is such that the wavelength is some integral multiple of the length of this trace, then you're going to get some either constructive or destructive interference, right? Depending on which one it is. So you have nodes and antinodes essentially. So these are actually some, even though the reflections are very small, there is still going to be some reflections, right? So that's why overall the return loss is less than minus 20 dB, which means it's matched. But there is going to be a little bit of reflections, and that's why you see these nodes and antinodes, because there is some reflection along the ends of these lines, right? Because they're not perfectly matched to 50 ohms. So that's the first part, designing the taper. The second part was, as I talked about, designing your radius of the bend. And so what do you find typically? Unfortunately, I didn't have the HFSS graph for that, but typically this is what it looks like. So if I do the same trace, so I have a 50 ohm here, 50 ohm here, characteristic impedance, and then if I try different radius of curvature, what I find is that if, say, I plot insertion loss versus frequency, what I find is that when I use a much more gradual radius of curvature, I have an insertion loss closer to 0 dB, which means it's being transmitted, right? And also, if you notice here, the insertion loss is actually decaying more with frequency, because when you go to higher and higher frequency, and the wavelength becomes comparable to this bend dimension, you're getting more radiation out of the bend, right? So when the bend is sharper and as the frequency is getting higher, the insertion loss is suddenly decaying very fast because you have a lot of signal that's being radiated out from this line, okay? So what do? You basically do different radius of curvature and you see how the insertion loss is, right? And then I think I settled on like 20 centimeter as my target radius of curvature, okay? Sorry, 2 centimeter as my target radius of curvature. So then the problem is essentially, I have the taper, so I know what is the taper length. At the same time, when I bend this line, I have to make sure that at any point, the bend radius has to be greater than 2 centimeter. Because if it's less than 2 centimeter, it's going to radiate significantly, right? So then it's really a question of optimizing this geometry so that at any point in this geometry, the radius is greater than 2 centimeter and the taper is as I designed, right? So if I put all that together, I get something like this, okay? So in this case, and actually, yeah, the radius of curvature is approximately the greater than 20 centimeters, sorry, 2 centimeter throughout the length of this trace. And then if you look at what the signal transmission looks like, you see how the signal is coming in over here. So this is from the SMA. And then because of the taper, it's being squeezed down. But because the bend is very gradual, you see that the signal is not being radiated out, right? Now, can someone tell me what this thing going back is?
I think it's cross couple, crosstalk.
Yes, this is the crosstalk. So you can see the crosstalk here. So what's happening is the signal is coming here, but as these lines are getting closer, they're capacitively coupling. So some signal is being coupled to this line, but that signal then goes here, reflects back, and then travels back here. Okay. So it's a combination of reflection and cross coupling. So you have this line, the signal is being coupled and then reflects over here and then goes back. Okay. So this is near end crosstalk. Sorry, this is, yeah, this is, wait. This is, yeah, this is near end crosstalk because you're looking at power over here and you're checking power over here, right? So you have, but you see, the most of the crosstalk happens in line 2, line 3 and line 4, not so much because they're more further away from this, right? So it's very sensitive to how close this line is to the aggressor, right? This being the aggressor. Yeah, so that's pretty much, like here's an example of how it can be done. This is a very simple case, but when you're an actual RF engineer, these things get very complicated and there's like a whole bunch of different kind of custom designs that people do to do this kind of matching and so on. So now, let's see. Yeah, there is time. Let me try to attempt to do this. So, before we go there, right, I think that's pretty much what I wanted, the main things to take away from this. You guys have any questions before I go on to the bonus lecture?
Is the first image that you showed with the in the case study, the actual geometry that you used?
No. This is just a diagram. This is just a representation. This wasn't the actual geometry. This is just a CAD drawing showing the full structure, but this is not the actual final structure that we have.
Got it.
Yeah. Okay. Any other questions? Okay, now let's go to the the most fun part here, the bonus lecture. Let's see how fun it is. But okay.
Welcome.
Yeah.
Yeah, one question. Yeah.
Does the thickness of the wire affect the radius of the bend?
Does the thickness of the wire affect the radius of the bend?
Are you talking from a processing perspective?
No, not really, no. See, the thickness there was selected based on what was available, okay? Because it was a PCB, it was a Rogers substrate basically. So I think it was like 18 microns. They had only like half ounce or 1 ounce copper is like 18 microns or something was the thickness. So I just stuck with that thickness. So yeah, unfortunately, this was not microfabricated. So I don't have control over what thickness I can use. It's whatever substrate is available. But shouldn't depend on thickness that much, because the thickness is very small compared to all the other dimensions, right? Thickness like 18 micron, and I think the lines are like 200 microns or something. Okay. Everyone good? Okay, this one is going to be a little hard pill to swallow, so please follow me. But so we're going to see how we can understand how to do matching. So how I can match any impedance, say ZL, to Z naught, right? Which is the characteristic impedance of the transmission line. And if ZL is made equal to Z naught, it's matched, right? So we are going to see how we can do this matching, but one of the best ways to understand how this matching can be done is actually using a trick. It's using a concept from complex analysis. And, electrical engineers know it as Smith chart, okay? But basically how it works is, imagine you had an impedance, right? So let's say some Z. So it has a real part, it has an imaginary part, right? The real part being resistance, imaginary part being the reactance, right? So here's the thing, right? You can either represent this impedance by R plus JX, but you can also get all the information that you need about Z by just seeing what is a reflection, right? So I can get all information about Z by knowing R and X, or I can just connect the transmission line Z naught here, measure the gamma, and the gamma itself has all information of Z, right? So for example, since gamma is Z minus Z naught by Z plus Z naught, and Z naught is just a constant, if I know the real and imaginary parts of gamma, that's equivalent to knowing the real and imaginary parts of Z. Does that make sense?
Yeah.
Okay. So essentially what we are going to do is we are going to map this complex number Z to a new complex number gamma. And if you look at this expression, and if you guys, I know you must have learned this in like undergrad, but does anyone know what this expression actually is mathematically?
You're like
Uh, sorry?
normalizing the impedance,
Sorry?
normalizing it.
Yeah, normalized. No, that we haven't got to that part, but this expression, right? So Z is a complex number, gamma is a complex number, right? So what this expression actually is doing is so imagine Z is a complex plane, right? Which the real axis being R, the imaginary axis being X. So what this expression is doing is it's taking every point on the Rx plane and then taking it to a new complex plane, which is the gamma I, gamma R plane. And this kind of expression is basically called as a bilinear transformation. Okay, so it's taking every point on Z to gamma, and this has a very unique property. The unique property is that it preserves angles. So imagine you had something that was at 90 degrees on your original complex plane, right, on the Z plane, then that 90 degrees is still maintained in the gamma plane. So that's a feature of the bilinear transform. Anyway, let's not bother about that. Since it's a bonus lecture, I can say whatever I want. So, yeah. So basically what we're doing is we're going to map this Rx to gamma R, gamma I, okay? So how are you going to do this? So remember that Z is R plus JX, but because we have this expression, from this expression, we can also calculate what is Z in terms of gamma, right? So Z is 1 plus gamma by 1 minus gamma times Z, right? So we have two expressions for Z. So we have Z as R plus JX, or Z is this. So you can equate this to this. And then if you equate the real and imaginary parts and then you rearrange, what you get is you get two expressions, okay? And if you look at these expressions, what they are is they are actually equations of circles, okay? So what is actually happening here is that the R and X, so the R and X are being transformed into circles on the gamma plane. Okay. So here's what it actually looks like. So let's say this is a Z plane, right? So this is the impedance plane. So these red lines represent different values of resistance, right? So say R equals 0, R, these are normalized to Z naught, but R equals 0, 1, 2, 3. And the reactances are the y-axis, right? So X equals 1, 2, 3 positive and X equals minus 1, 2, 3 negative, right? So this positive reactance, negative reactance. Why is this left half of the plane, nothing is there? Why haven't I considered that? Anyone?
Talk about negative resistances.
Exactly. You can't have negative resistance, right? Yeah. So it's only the right half of the plane. So if you use this expression, and I would again ask you guys to go back to this, derive it for yourself and see for yourself. But if you use this expression, what you'll find is that these red lines are essentially transformed into circles on the new gamma R gamma I plane. Okay. So R equals 0, this line basically becomes this circle over here. Okay. And R equals 1 becomes another circle like this. And R equals infinity essentially becomes the point here. Okay. Similarly, the same kind of transformation also holds for the x's. So for example, x equals 0 is essentially becomes the y-axis itself, x equals 0. And then x equals infinity becomes the point here. Okay. And anything in between. So for example, you see how x equals 0.7 is here, x equals 0.5 is here, and so on. Okay. So these x and y axes are essentially transformed into a bunch of r and x circles right here. Does this make sense? All I'm doing is I'm just taking lines in one coordinate and transforming into circles in the other. Okay. And this kind of transformation happens because of the expression, right? Z minus Z naught by Z plus, sorry, ZL minus Z naught by ZL plus Z naught. The effect of that is it takes an impedance which is in the rectangular space, something like this, and transforms it into circles, something like this. Okay. So imagine let's say I had a constant resistance, right? So imagine my resistance was 1 or R equals 1. But let's say I want to change my reactance, right? So I have the same resistance, but I'm changing my reactance. Then what that actually means is, in the same way, like say R equals 1 and X is changing, what does that mean? I'm moving up and down in this R equals 1 line, right? Equivalently, what happens here is you are not moving in a line anymore, but you're moving in a circle. So you're moving on the R equals 1 circle. And as you're moving in the R equals 1 circle, you're going through different X circles, right? Which is equivalent to X changing, right? And the reason why this is bilinear is because if you notice, these angles are 90-degree, but these angles are also 90 degrees. So if I look at the angle between this circle cut here and this circle cut here, it's also 90-degree. Okay, that's why it's bilinear. Similarly, so this is for impedance. You can similarly do something for admittance and you get its own set of circles. And then you can kind of superimpose both. And that's what essentially the Smith chart is. Okay. Now, whether you understand this or not, what is the important thing is if I want to match ZL to Z naught, that's equivalent to what? If ZL equals Z naught, gamma is 0, right? So the matching essentially becomes how I can go to this origin, right? So if say I have an impedance that is somewhere here, which is some resistance and reactance, if I can do something to bring it all the way to this origin, then essentially I've matched ZL to Z naught, okay? And that's how Smith chart is often used in practice. So, and I think I don't want to go too much into details because it's quite involved, but yeah, but what happens is by adding a resistance or a capacitance, you can actually move different ways in this space, okay? So for example, imagine this was your ZL, right? So this was your load impedance. So in order to match ZL to Z naught, you need to move the ZL all the way to the origin, right? So because gamma equals 0. So first you move along this circle, then you move along this circle. And then you can show that in order to move like that, the only way to do that is to add inductance in parallel and a capacitance in series. Okay. And so by using the Smith chart, you can actually calculate what is the value of this inductance, what is the value of this capacitance that you need to add so that you can bring this ZL all the way to the origin, which means it's matched to Z naught. And it turns out there are many ways to move. So for example, in this case, you move this way. You first go to this circle, then come this way. There are other ways to move in this space, and that corresponds to different kind of elements that you can add to match it to Z naught. Okay. And there are also very other complicated ways that you can move in this space, which basically ends up having to add different components in series and parallel. Since we ran out of time, I want to stop there. Okay. But if you guys are interested, you can always read a microwave text and you can always go through this.
All right. Thank you. With that, we will end the class. But again, the homework is due next week, exactly a week from today. And if you have any questions, reach out to Gautam by email or something like that. You'll definitely be able to answer. Thank you.